In the last few videos, we've taken our x-bar values, our standard deviation of sigma, our sample size of n, and some error level, or alpha, to create a confidence interval for our population mean. So to do that, we had our x-bar, then we added and subtracted our z value, which was associated with our alpha, so alpha over 2, and then we multiplied that by our population standard deviation of sigma divided by the square root of n, or the square root of our sample size. And this gave us some region in which we can be confident with some error that our mean would fall within some bound. But what if instead we wanted to determine the sample size we needed, so that n value, for a given bound size? So say we wanted to find how many samples we needed to make for our error window to be a certain size. So to do that, we just need to look at our right side of our equation over here, our z alpha over 2 times our sigma divided by a square root of n, because that's what's creating that error size. So we're going to call this our margin of error, or ME. So ME is equal to z of alpha over 2 times sigma divided by the square root of n. So if we're trying to get that sample size, n, we can multiply the square root of n to both sides and divide both sides by the margin of error. So we have square root of n over margin of error, which we're multiplying by on both sides. So that gives us our square root of n on the left equals our z of alpha over 2 times our sigma divided by our margin of error. So we have sigma over ME. And then we just need to square both sides. So if we square both sides, we get n is equal to, we can just rearrange this a little bit, z of alpha over 2 times sigma over our margin of error, and that whole quantity squared. And that'll give us our sample size necessary for a specified margin of error. We can also calculate a specified sample size based off the margin of error for a proportion. And it's just using the same formula. So we have our z of alpha over 2 multiplied by p times q over n, square root of that value, is equal to our margin of error. So if we rearrange all that to get n alone and on one side, we just get n is equal to, we have z of alpha over 2, and that quantity is squared, multiplied by p and q, and then that whole quantity divided by our margin of error squared. And that'll give us the sample size necessary for a specified margin of error for our proportion values. So let's use this to try to find the sample size needed for a specific experiment. So for our experiment, we're trying to find a 90% confidence interval, which makes our alpha equal to 0.1, which means we get a z sub alpha over 2 of 0.05, which is equal to 1.645 standard deviations. And our sigma for our population is equal to 10. And we want a margin of error of 5. So we want our x bar plus or minus 2.5. So to calculate that, we have our formula. We have n is equal to our z of alpha over 2 times our sigma, and then that is divided by our margin of error, and that whole value is squared. So that gives us, we have z of alpha over 2 is 1.645, so we have 1.645 multiplied by sigma, which is 10. We have our margin of error, which is 5, so we have 5 on the bottom. And then we have that quantity squared. And then if we look at that, we can cancel these out. We have our 5 and a 10. So we have 5, 10 cancel. We just have 2 up top. Then we have 1 on the bottom. So that turns into 1.645 times 2, and then that whole value squared. And then that gives us 1.645 times 2 is 3.290. And then 3.290 squared is equal to 10.824, which turns into 11, since we can't have 10 point something number of samples. So if we have a population with a standard deviation of 10, and we're looking for a confidence interval of 90%, so 10% error, 5 on either side, with a margin of error of 5, we need to take 11 samples, and then that will give us the appropriate margin of error with that information. For our proportion example for determining sample size, we're going to look at political polls. So for most political polls, they're looking for a margin of error of 3%, so 0.03, and they're looking for a 95% confidence interval, which turns into alpha is equal to 0.05. So we're going to get a z of 0.025 is equal to 1.960. And for this, we need to know P and Q, probability of success and probability of failure. So we're just going to assume each candidate has a 50% chance of winning. So we're going to do 0.5 is P, which turns into Q is also equal to 0.5. So this could change a little bit depending on who's most likely to win and by how much. So to figure out our sample size, we have N is equal to, we have our Z of alpha over 2, that quantity squared, times P times Q, and then that divided by our margin of error squared. So if we look at what that equals, we have Z of alpha over 2 squared, so we have our 1.960, 1.960 squared, times P times Q of 0.5 times 0.5, or 0.25, and then that divided by our margin of error. So we're looking at a 3% margin of error, so we have 0.03, that value squared, and that gives us 1.960 squared is 3.842 times 0.25, all over 0.03 squared is 0.0009. So we get 3.842 times 0.25, which gives us 0.9605 over 0.0009, which turns into 1067.2. So again, we can't have a fraction for a number of samples, so we have 1068 people that, if are sampled correctly, will give a good 95% confidence interval with a margin of error of 3%, estimate as who's going to win any political election.